Welcome to the Intel Hyperflex Architecture Overview online training. My name is Marlon Price and I will be the presenter for this training. By the end of this course, you will have an understanding of the features that make up the Hyperflex architecture, and you will understand how these features will allow your designs to achieve clock speeds of up to 2 times over the clock performance possible in prior FPGA architectures. We will begin this training describing the new Hyperflex architecture and its advantages. Then we will address a few questions that commonly arise after learning of the new architecture. Lastly, we will do a brief overview of how designs can be optimized to take advantage of this architecture. More details on this optimization flow will be covered in additional online trainings similar to this one. So let's begin with a look at the Hyperflex architecture. Traditional FPGA architecture is already register heavy. There are multiple registers in every logic cell, as well as registers in I/O, multiplier blocks, memory blocks, and dedicated hard IP like transceivers. This is a conceptual diagram showing a conventional FPGA architecture. The FPGA structure is mostly made up of logic cells that are used to implement general logic functionality. These logic cells are called ALMs, or adaptive logic modules. To connect the output of one ALM to the input of another ALM in another area of the device, the signal would have to go through multiple row and column resources as shown here. Though we're only looking at ALMs here, all device structures, including multipliers and memory blocks, would be connected using the same strategy. If a pipeline register stage is to be inserted in the path between two ALMs, then the signal path between them must take a detour through an additional ALM in order to make use of that ALM's registers. Unfortunately, there is an expense to using an ALM register for pipelining in the form of a significant increase in the delay of the timing path. Now, the actual delay incurred depends on the particular target device, but in general, each time the signal leaves the row and column resources to go into an ALM, it encounters an additional delay from the local routing needed to feed the ALM itself as the signal passes around the lookup table or LUT, and the local routing to exit the ALM back to the row and column resources. As a result, these delays have the effect of limiting how many actual pipeline stages can be inserted in the path before no more clock performance improvement is gained. The Hyperflex architecture introduces even more registers throughout the core fabric. The key building blocks for the Hyperflex architecture are bypassable hyperregisters located in every routing segment and at all block inputs in the core. Unlike existing architectures, this is a more fine-grained approach because there are really hyperregisters located everywhere throughout the core fabric. This means your design has many more options for inserting register stages than before. As a result of this fine-grained approach, the Hyperflex architecture enables 3 key performance improvement strategies, which we name Hyper-Retiming, Hyper-Pipelining, and Hyper-Optimization. To look more closely, there are bypassable hyperregisters and the routing muxes. This means that as a signal moves between any row and column resource, there is an option to register or not register that signal. There are bypassable hyperregisters on the inputs to all block structures. For example, ALM lookup tables, ALM registers, multiplier blocks, and memory blocks. And all of the individual ALM registers are bypassable. This means that instead of registering a signal in an ALM, that registering can be done downstream in a more ideal hyperregister location for timing. But the ALM's control signals could still be used by that downstream hyperregister. You can see more on the impact of this architectural feature in follow-up online training. Here is a representation of the Hyperflex FPGA architecture showing the Hyperflex registers as the orange squares. As you can see, the Hyperflex architecture provides an abundance of hyperregisters located conveniently around the device to maximize design performance. In fact, with the Hyperflex architecture, there are 10 times the number of hyperregisters as there are conventional ALM registers. Thus, to follow the same path as we showed before from one ALM to another ALM, the signal path has a huge number of locations in which it can pass through a hyperregister. Let's follow the same path. Now, let's follow another path. In both paths, and any other path you may draw between the two ALMs, choosing a register location for a pipeline stage is much simpler than before. So as a result, pipeline stages can be added virtually anywhere between the two logic structures. And this can be done without incurring the timing delay of using a register in an ALM to do the same thing. In effect, registers become cheap as the cost of adding them to a signal path has been eliminated by the architecture. And thus using these hyperregisters is really the formula for achieving the highest possible performance in the device. This brings up some common questions on the architecture. Let's address those now. With the addition of all the hyperregisters to the architecture, how does this affect power? Well, the hyperregisters are simple D flip-flops, so each requires only a few transistors to implement. This is less than the number of transistors required to implement an ALM register with its flexible control signals, much less than the number of registers required to implement more complex blocks like the RAM and DSP blocks, and significantly less than the number needed to build transceivers or hardened memory controllers. As a result, the hyperregisters collectively contribute minimally to the total static power. With regards to dynamic power, hyperregisters on their own do not cause an increase in power. This is because during optimization, the software tools take register stages implemented in ALM registers and replace them with hyperregisters. Overall, this proves to be more efficient than using other ALM registers for the same type of optimization. Keep in mind, though, that since the hyperregisters do enable designs to go faster, increasing the clock speed of your design will cause the dynamic power consumption to scale with that frequency increase. But using a power-efficient 10 nanometer FinFET process technology from Intel and other architectural optimizations results in the device family designed to balance performance and power consumption. With traditional FPGA architectures, registers are designed for no hold time issues, assuming dedicated clock trees are used correctly. But with all these hyperregisters everywhere, aren't hold times going to become a problem? Well, with this increase in speed comes a location rule. You cannot enable adjacent hyperregisters everywhere in the device. So looking at the example diagram here, we cannot enable all three hyperregisters to connect these 4 row channels in series. Now the exact number of adjacent registers that cannot be enabled depends on the specific routing resource being used. For the shortest routing channels, the restriction may mean 2 or 3 adjacent registers. For the longest routing channels, there would be no restriction at all. To understand this, you must first consider why there are so many hyperregisters in the first place. The point is not so a user can enable all of them at once. The point is so the compiler has lots of options for placing a pipeline register. So the compiler can really choose the ideal location for that register with respect to timing. And since the Quartus compiler is aware of this location placement restriction, it will ensure adjacent hyperregisters are never enabled. So if you are a user, you don't have to worry about this rule at all. The location rule ensures that hold time margins are met between hyperregisters. But these situations can arise. What I mean is that there are certain situations where the compiler wants to enable a hyperregister, but it cannot due to this location rule. If this occurs, it is reported in the fast forward compile report. This report and what to do when a situation like this arises is discussed in follow-up online training. The last questions have to do with clocking. Will the traditional FPGA clock tree support all of these registers? With the new Hyperflex architecture comes a new synthesizable and programmable clock tree. This clock tree is synthesized locally during compilation to build a tree only where it is needed. This provides less variability and lower clock skew over a traditional global clock tree, enabling clock rates up to 1 GHz. The new clock tree is also more flexible. Instead of a clock tree pre-built in silicon, the clock tree is more similar to the row and column resources in that there are dedicated clock routing segments throughout the device that can be stitched together to create a clock region. The result is that you can have a greater number of clock regions than before and up to 32 independent clocks in one section of the chip. Because the new clocking structure allows for smaller and more focused clock regions, you can have lower clock tree power dissipation due to less switching capacitance and branch disabling. I'll show an example of this in the next two slides. And the clock tree is backwards compatible, so if needed, the clock tree can be synthesized into true global, half-chip, and quadrant clocks to which FPGA designers are familiar. Also, though architecture diagrams show the routing channels between ALMs, the physical FPGA is made up of layers in silicon. So rather than the routing channels being between ALMs, the routing channels, including the clocks, actually run over top of the ALMs as well as the hyperregisters. So it is not necessary to expand the clock tree to connect to the additional hyperregisters. They simply connect to the clock tree that's around them already. Let's do a quick comparison of conventional clocking versus the new synthesizable clock tree. With the conventional FPGA, the clock tree is divided into global clocks that drive all areas of the chip and regional clocks that reach a quadrant of the chip. If a logic cloud straddles two quadrants, like pictured here, this would require enabling a global clock. Note this could be done also with a dual regional clock, which makes the use of two adjacent regional clocks. If the fitter chooses to place logic running off of a second clock into two discrete areas of the FPGA like shown here, the only way to reach both areas would be to enable a second global clock tree. And finally, another logic module running off a third clock is placed within one quadrant of the chip. To reach these registers, a regional or quadrant clock could be enabled. But in each case, you see that there are large sections of the FPGA where the clocking resource is enabled, but in which no logic is actually running off of that clock. Since the entire clock tree is enabled and powered, this translates to additional power consumption for the device. Now let's look at the programmable clock tree synthesis. This clock tree is composed of segments that span the FPGA's XY coordinate system, creating clock sectors. The clock tree is only synthesized to the sectors where that clock is needed to drive logic placed in that sector. For clocking the first module, instead of using an entire global or two regional clocks, the clock tree segments are synthesized to encompass only the area that is needed for that module. Again, for the second module, the clock tree can be synthesized to drive only the necessary logic. Even though the fitter may rarely split a clock domain in this way, it is not a problem to synthesize the clock tree as needed to drive those registers. And finally, for the last logic cloud, instead of using an entire quadrant clock as before, the clock tree is synthesized to a region even smaller than a quadrant. In all cases, the unused parts of the clock tree are limited. Now that I've covered all of the architectural information, I will talk about how you can target a device with the Hyperflex architecture with your design flow. To extract the most benefit from the Intel Hyperflex architecture, Intel FPGA has defined a three-step process that you can follow, consisting of hyper-retiming, hyper-pipelining, and hyper-optimization. Depending on how your design is coded or structured, significant performance improvement is possible in any of the steps. But in general, as you move from one step to the next, the performance of your design grows as well as the design effort needed to implement that next step. The three steps are hyper-retiming, hyper-pipelining, and hyper-optimization. The first two stages are based on well-understood design techniques commonly used by design engineers today to improve performance. Many times they account for most of the performance gain in the three-step process. So some designers can simply stop after implementing hyper-retiming or hyper-pipelining. But in cases where a designer wants to achieve even higher clock speeds, then the designer can move on to the final stage, hyper-optimization. This stage may require more dramatic restructuring of the design based entirely on its functionality and how the RTL is originally coded. It is important to remember that you, as the designer, can choose whether to implement these techniques separately or globally depending on your design and your performance goals. Though retiming, pipelining, and more advanced optimization will see performance gain when used in any FPGA today, their results when used on the Intel Hyperflex architecture are much greater. Again, the Hyperflex architecture was designed with these optimizations in mind. So how do these strategies work? Stage 1 is hyper-retiming. Hyper-retiming involves moving existing registers in your design from ALM locations into hyper-registers to cut critical paths and improve overall performance. This is done automatically by the software. But in some cases, due to the architecture of the hyperregisters, it may not be possible to move ALM registers. So hyper-retiming may involve removing certain restrictions that would prevent ALM registers from being retimed into hyperregister locations. Stage 2 is hyper-pipelining. Hyper-pipelining involves adding new registers to the design RTL so that they can then be retimed into hyperregister locations. This cuts critical paths even more as there are more overall registers in the design, so the individual register-to-register paths in your design can be reduced even more. Stage 3 is hyper-optimization. Hyper-optimization mostly involves loop management, or restructuring design loops to lessen or eliminate the negative impact they have on performance. Using hyper-optimization allows you to take your design performance beyond the effects of hyper-retiming and hyper-pipelining alone. So this concludes our look at the Intel Hyperflex architecture. As you can see from this training, the hardware changes available in the Intel Hyperflex architecture enable designs to achieve higher performance, on average, over previous FPGA architectures and generations. These hardware changes include hyperregisters on routing channels and on block inputs, bypassable ALM registers, fast bypass paths when hyperregisters and other ALM resources are not used, and finally programmable clock tree synthesis. To take advantage of the architecture, you as the designer can employ the design techniques of hyper-retiming, hyper-pipelining, and hyper-optimization. Intel provides multiple avenues in which to learn about Intel FPGA products. There's the Intel FPGA YouTube channel, which contains 5-minute quick videos along with longer, more in-depth training videos. There's the Intel FPGA training website, where you can access e-learning courses made up of narrated slides presented in an interactive player, some courses even with labs and demos. Lastly, you can enroll in a live instructor-led course presented either in person at an office local to you or virtually over the web. All instructor-led courses have hands-on lab exercises to practice the concepts you learn. If you need more assistance, Intel FPGA provides many self-help resources for you to access. For example, there are web pages called landing pages dedicated to specific FPGA technology like external memory interfaces and high-speed protocol interfaces. You can also view and post questions to the community forum, which is monitored by skilled Intel FPGA applications engineers. The Intel FPGA training team is always looking to improve our material. To do this, a survey will be emailed to your registration email address. We welcome any feedback you may have. This concludes this online training. Again, my name is Marlon Price, and I thank you for attending.